recording. So recall yesterday we were looking at our W linked list, and we talked about how we could do insertions into that list, and then how we could do a removal into that list. So just to remind us, an insertion, we have here three elements with, or three nodes in our list, storing elements A, B, C. If we wanted to insert a new node after node P, then we would get that new element that we want to store, create a new node, store that element in it. All right, this happens to be element X. We then update the references of our new node for its previous to point to P, for its next to point to whichever node is storing C, so the one that was previously after node P. Then we update the node that came after P, because we still have reference to it within P. We update its previous to now point to the new node Q. And finally, we update P's next to refer to that new node Q. That then gives us the new list with Q within that, with all our references now correct. All right, there are some questions in there. Someone's talking about soccer. I have no interest in that. Then recording, yes, we are recording that. Please answer the question at 12:09. I did answer that. You have to keep a record of head. Right? Is there a reason we keep our header and trailer empty with W linked lists? Yes, there is a reason. The reason we do that is that these are not actual nodes that are going to store information, that are going to store elements. Instead, they work as sentinel nodes. They allow us to, well, firstly, ensure that we always have a previous and a next for any of our real nodes, so that we can always add after and before. Rather, when we implement the methods add after or add before or add between, we know that whatever node you're busy with will always have a node before it and a node after it, because it'll have those sentinel nodes. So they make our methods a lot easier. And of course, then you can check if you're at the end of the list or the beginning of the list by checking, well, is the previous equal to the sentinel node header, or is the next equal to the sentinel node trailer? Right, so it makes our methods simpler, or they work for all of our nodes. With a single linked list, you'll see that you have to check. I can't assume that I can add something before my head, and I can't assume that there'll be some next for my tail. And a question, other lectures, Gadel, Red, Laser. Okay, whatever that may be. So in a W linked list, we start on the P side, then Q, unlike in a singly linked list. Well, you recall that when we defined our list ADT, right, we're looking at, well, what should anything that implements list be able to do? What behavior should it have? Let's just go back to that. We said that it should have the update methods insert before, insert after. So we should be able to do either of these inserts. An insert after is easy enough whether we're working with a single linked list or a W linked list. However, the insert before is rather difficult for a single linked list, because you don't keep a reference to whatever element occurs or whatever node comes before the particular node that we pass. Whereas a W linked list, because we keep that previous reference, it's a lot easier. You can again do it in constant time. All right, so that question of, is it that we're doing it on the P side, the Q side? We should be able to do both sides. We should be able to add after and before a node. For a single linked list, the header and the tail must be able to hold. Okay, stop right there. It's not the header. In a single linked list, it's the head, which is a reference to the first node within that list. And that is a normal node that stores some element. So if the list were empty, head would then refer to nothing, right? Would refer to null. If we're talking about the sentinel nodes within our W linked list, then the header would not store anything, the trailer would not store anything. When would we like to use a single linked list over W linked list? Well, let's say that we wanted to conserve space within memory. We understand that for a doubly linked list, each node will now store an additional instance variable that stores a reference to the node before it. So singly linked lists are more efficient in terms of space. However, our doubly linked lists have methods that are constant time. So that means that if you want to use a singly linked list to implement something like a stack, or we saw with a queue, then it would be smarter to use a singly linked list because it will suffice. For a stack, I can insert and remove from the front in constant time. I don't need to use a list that now stores all these unnecessary references. Right. So what would an algorithm for that insertion look like? If we want to insert an element E after a node P, then we'll create a new node. Here we call it V. We then set the element of V to be E, so we store E within that new node. We then have to update the previous and the next of V. We do that first before we change the next of P or the next of what we called, well, no, the Q was the new one. So before we update P's next or the previous of what used to be P's next, the node that came after P, we first update V's next and previous. Because if we were to first update those two to point to P, we would not have, or to point to this new node V, we would no longer have references to those. So we first update V's previous to P, great, because it's going to come after P. We then update V's next to P's.getNext, so the element that was next after P within our list before we inserted V. Then we update the previous of P's next. So again, that one, the node that was a successor of P will update its previous to be V. And we then update finally P's next to be V. They've updated 4 different references, the 2 new references of the previous and next for V, and then P's next and P's next previous to now both point to V instead of initially P pointing to P's next and P's next pointing to P, all right, as its previous. You could make this a little simpler by using a temporary variable P next or whatever you want to call it, maybe Q, storing, allowing that to refer to P.getNext. Then you understand. If I'm trying to insert something between P and Q, it's a lot simpler. So I can give a hint that tomorrow is practical. I've already given a hint. We're going to be doing singly linked lists. To give hints regarding the main methods, I assume you're in the groove of things now, right? You already know that you're going to have to work with files for most of them. You will be asked to work with the user interfaces sometimes, but you should be able to, given a problem that's described to you in a series of methods, implement those methods. And really, it isn't something that requires new knowledge from you. This is all assuming the knowledge from last year, but applying that to now solve problems using these. Some of these data structures are going to be new, but thus far, data structures that you are comfortable with. All right, but we walk you, as before, it'll be separated into methods. You'll get most of the source code. You simply then have to implement specific methods. All right, then to remove a node. So our linked list, or rather our list ADT, also had a method remove P, so we should be able to remove an arbitrary node P from our list. So how we do that for a doubly linked list? Well, basically what we want to do is we want to be able to take here this node that we're storing C, update its next to now refer to the node that occurs after P, update that node that occurs after P to have its previous now point to the node that occurred before P, then to be pedantic, we'll then remove those references from P to its previous and its next. So we'll set those to null. This essentially cuts P out of the list, and so we know it'll be collected by Java's garbage collector and has now been removed from our list. Usually you'll want to return whatever element was stored at it, so we will perhaps create a temporary variable and we'll store within that D, and at the end of our method, we will return that value. All right. So this is what we do. We first update those two references to now no longer point at P. Then essentially we have a list that does no longer have P in it, regardless of how that's stored in memory. And this is what the algorithm will look like. So we give a reference to node P, and we want that node to be removed from our list. First, we store its element in a temporary variable, so we can return that at the end of our method, there at line 7. Again, you could create temporary or local variables of top node to be able to store P's previous and P's next to kind of clean up the look of it. But essentially, within parentheses there, p.getNext is now referring to that element that occurred before P within our list. We want to change its next to no longer refer to P, but instead to refer to P's next, so to work P out of the list. We do the exact same thing with P's next. We change its previous, so we refer to it with p.getNext. Then we set its previous, .setPrevious, to the node that occurred before P, so p.getPrevious. That essentially works P out of the list in the reverse direction. Then we set P's next and previous to null, and then we return that T. All right. So there's a question for the single linked list. In add last E, the second last step is set variable tail to reference the new node. What does it mean? Please may explain using this diagram. All right. Let's go back to that initial diagram. All right. So remember, we have these central nodes, header and trailer, but we also store a reference to our head, right? Especially in the single linked list, because we have to have a reference to head, and we can have, and we do by convention, have a reference to tail. Now, if we were to remove last, right? Oh no, there was add last. So if we were to instead add a new node here, right, regardless of whether it's a single or double linked list, it's storing something, let's say D, we've added a new one here. I'll just give it a second, I know the annotations don't come up right away. Then if we were to leave tail referring to the node storing C, tail would no longer refer to the last node in our list. It's a single double linked list, and that's wrong. We have to update it. We have to now set tail to the new last node because we're adding something at the end of our list. All right. Then why is life so difficult? Because you think it's difficult. Can the remove method be a procedure instead of a function? Yes. Right. You learned that from first year that any function can be implemented as a procedure. Then you'd simply pass it a reference to that variable that you want to store the element that you would have been returning. So certainly you can. So to execute linked list, okay, implement, I assume you mean, we can define a class which inside of it has an array of nodes and methods to traverse and add nodes. What are many ways of executing? Okay, there are many ways of implementing a list. Remember, a list is not a concrete data structure. A list is a description of, what we said in ADT in general, is a description of data that's stored and methods to manipulate that data. In Java, we have an interface. It doesn't tell you what data you can store, but instead just the behavior. So that's how we realize an ADT in Java. And so anything that implements that list interface, which is the representation of our abstract data type in Java, will then be a concrete implementation of that list. That, yes, there are many different ways to implement that. We could do it using an array, but we realized that we'd have to shift things left and right when we do removals and insertions. We could use a single linked list, and we see that now we could use a double linked list as well. We're talking about a linked list, but storing that as an array of nodes. Well, a linked list is a concrete data structure where you have nodes and links between them. That's not an array. Right? Those are two different concrete data structures. Yes, we will sometimes use an array together with a linked list. Later, when we get to iterators, which you may not have discussed before, then we want a systematic way of being able to traverse and return all the elements within our linked list. And because the way that Java looks at iterators as these single shot ones where we simply return what the values were at a single instance, then yes, we would usually use an array for that. But we'll get to that. All right, so what is the advantage of using a doubly linked list to implement our list instead of a single linked list? Well, remember with the single linked list, we found that most of the methods were constant time, except for certain accessor ones like previous p, and certain mutator ones like remove before, right, or add before. So now what we find is that with our doubly linked list, it's still big O n in terms of how much space it uses, because any multiplier falls away in big O notation. You may not remember that, but we will go over it again when we get to that point of discussing computational complexity. So they're both linear in terms of the space that they use. The space used by each position is again constant. However, now all our list operations run in constant time, not just most of them. And of course, again, the element operation, which is the only operation of our position ADT, that runs in constant time. All right, let's not just accept this, let's go and convince ourselves. Okay. What is the difference between a doubly linked list and a skip list? A skip list is very different. All right. So oftentimes, what's most important for us is to be able to retrieve things within a data structure, quickly retrieve them, right? So a skip list allows us to be able to quickly get to things by, given an original list, we create many more lists by each time randomly deciding whether or not we should add the elements of the previous list to the list above it. So that first list we take as level 0. For level 1, we flip a coin, which has a probability of 50-50 landing on heads or tails. If it's a heads, for example, we'll then add that node or that element, let's keep it general, that element to list L1. We do the same thing over and over and over. We should then have half the number of elements within each list. And then by following a fixed rule of how we traverse that skip list, we're able to get to any element within that skip list in log n time, which is a lot quicker than getting it in linear time. All right. Yes, the question that was asked there, we'll go and convince ourselves of right now. So let's go back and look at that description of operations that define our list ADT and convince ourselves that with a doubly linked list, each and every one of those can now be done in constant time. So first, yes, certainly, right? Whether we return head or simply head is next, either way, that's constant time. It's one or two operations. Last, yes, tail or tail is previous, that's constant time. Previous p, give me a reference to p, I just return p dot previous. Great. Next p, given a reference to p, I simply return p dot get next or p dot next if I direct access to it. Replace pe, that's very simple. I simply access the node and I can replace or set the element of that node to E. Then insert before, well, if I have access to P and I can get to the node that occurs before it, then I can update that node's next and P's previous to be able to add a new node between them, and I set that particular node's element to E. Right, very similar to the insert after that we looked at just now. Insert after we looked at it, its method implementation, or at least that pseudocode that we looked at, does not rely on the size of, or it's not dependent on the size of the linked list itself. It is that same number of operations, create a new node, store E in it, update P's next, or rather first update P's next previous, updates P's next, and then update the two references that the new node has. Insert first, just a simple create a new node. We have the reference to head. We can update head's previous and also the head is next. It's as simple as add before head. Brilliant. Insert last, insert after tail. Brilliant. And remove P, we just looked at that. So all of these can be done in constant time. They don't require us to actually traverse the entire list, each time link hopping to get to a particular point where we can now update next. So this is preferable. A doubly linked list is preferable than a singly linked list when we are trying to implement a list. All right, and we should be convinced by that. Great. So oftentimes, or rather there are certain use cases where we will take whichever the current node that we're busy with, which is usually at the front of our linked list. We will then want to remove that particular node and add it to the end of our list. The use case that's described in the textbook is that of a round-robin scheduling. So is that a round-robin scheduling? We all know that nowadays we have machines that have multiple cores or sometimes even multiple CPUs with multiple cores or with multiple cores within those. But before we even had multi-core machines, we already had the idea of being able to run more than one application at one time. Okay, I'm not talking about multi-threading where we have, or hyper-threading where we have duplication of certain circuitry within our CPU, so we can do things like add more than one number at once. But instead, when we had just a single ALU, a single copy of the specific registers that we need to be able to access some point in memory and do calculations, we're still able to do more, to have more than one application running at one time. And how do we do this? Well, it's very similar to how you do more than one thing at a time. All right, think about when you're eating and talking, or perhaps you're doing your homework and you're watching TV. Are you actually doing those two things at the exact same time? Yes, you just context switch really fast. Exactly that. If you actually try to eat and talk at the exact same time, you choke, right? If you try to watch TV and do your homework at the exact same time, neither of those things are going to be done properly. So instead, you eat a little, talk a little, eat a little, talk a little. You do a bit of your homework, you look up, you're watching TV. Do a bit of your homework, you look up again. You do those very quickly, and it seems like you're doing both things at the exact same time, but you're not, right? Because you only have the circuitry, right, within you to be able to eat and talk one at a time, not at the exact same time. So the same thing would happen within these machines before we had multiple CPUs or multiple cores. You would store the context of an application, which is, well, whatever it has stored in memory, which includes the program counter. So where are we within that program? What's stored within the registers and some other information. We would then write that to memory, then read in the next application, let it execute for just a couple milliseconds, then switch again to the next one. So each time we're actually storing the state of an application, then we give the next application a turn. And so if we had just a regular linked list, which each node represented the context of an application, we would give an application a little bit of time to run, then check, have you finished execution? If you have, we remove you from the list. But more likely than not, you haven't. So we remove you from the head of the list, add you to the end of the list as the new tail, and then give the next new head some time to run. This is quite inefficient because each time we have to update all these references, each time we remove that node from the beginning of our list and add it to the end. So instead we can use what we call a circular linked list, where instead of keeping a reference to a fixed head and a fixed tail, we simply keep a reference to what we call a cursor, which tells us where we're at in that list. When we get to the end of our list, well, that is simply linked to the beginning of our list, so our cursor can advance once more to get to the next place. And by advancing that cursor, we're effectively removing what was the previous head and adding it to the tail, because it's now at the end of our list instead of at the beginning, just by moving one point forward. All right, and for those of you who've worked with relational databases, you may be comfortable with the idea of a cursor. It's a structure used to be able to traverse the results of a SQL query. So you may have come with that idea before. All right, so before we just move on, I'll answer a few questions. Would we need to loop through all the nodes to get the size of the linked list? No, we should be keeping. Size should be an attribute of a linked list, and we should be updating it either to increment or decrement it when we add or remove things. All right. Insert first means inserting before header, no after header. Right? Header is always before the first node within our linked list. We're going to have to do the code implementation of each of the data structures. You're going to have to do a little bit of it. All right. We'll try to give you some methods that aren't contained within the text or within the slides, but sometimes we will have some where you already have the pseudocode or we've discussed it already. You're simply implementing that. So you won't be doing all of it. You'll be doing a little bit of it. Okay. Yes, someone already answered that. Thank you very much. All right. Someone said, so no head, but the diagram shows a head. This one. Yes. Well, the idea was that initially we had a normal linked list. If we were to keep that reference to head, then we would have to update that, remove the one that was previously there, add it to end the list. But now using head instead of as something that represents the first node in our list, but rather as a cursor, which we're going to change its name to, then we don't have any end of our list. We don't really have any beginning. We use simply a single reference as the cursor that tells us where we are within that. Okay, so the image simply shows that conversion from the idea to a single list, to a list that has a single order from front to end, to now one that has a circular links and has simply a cursor. So we still have some methods like add and remove. However, now we simply have advanced sort of add first and add last. You can add anything anywhere, but then to update as you are done with one node and moving on to the other one, you will advance your cursor to the next node. All right, and we also find that with the doubly linked list, if we want to sort the elements contained within our list, it's a lot easier for us to have a doubly linked list rather than a singly linked list. Just think of the insertion sort that we discussed yesterday, where the idea is that we want to keep the left part of our list sorted, and so we move from the very first element across, and each time checking, is the current element, as in the element stored at the current node, at the right position within the list to the left. And so we want to advance to the right to consider the next current node, but we also want to be able to traverse to the left of our list to check, well, is this current one, let's say we're sorting in ascending order, is this current one smaller than the one before it? No, it's not. All right, then it's in the correct place. Perhaps it was. Then we check the next one. Is it smaller than the next to the left, the next to the left, the next to the left, until we find one where it's larger than the one to the left, and then we simply do an insert after of that one over there. All right, so it allows us to be able to easily move backwards and forwards in the list, and so algorithms like an insertion sort become a lot simpler. All right, so that is our discussion on linked lists. We have already, or you have come across them before, but now we've seen that these two different concrete data structures are useful implementations of our list ADT, but we see the doubly linked list is more efficient in terms of constant time execution of methods, whereas our single linked list, it uses less space, though it's still linear, still order n, but some of the methods like previous, like insert before or add before, are not constant time. They depend on the size of our linked list. All right, so we want to now move on to a new topic of recursion. Again, it's not a new topic, but we want to discuss it a little more in depth. One question before we do, does a circular linked list use more space? Well, compared to our doubly linked list, we have two more references now, but we have gotten rid of a whole bunch of things. We've gotten rid of the reference that would have been the tail. If we're talking about doubly linked list now, also the header and the trailer, because our list no longer has any beginning or any end. So it ends up actually using a little less space. All right, so what do you remember about recursion? Could you give an application of a circular list? Yes, I did. Round robin scheduling. All right, so what do we remember about recursion? Why do we have it? Why is it useful? Okay, so recursive method is a method called itself. Brilliant. Will tomorrow's prac use recursion in conjunction with singly linked lists? Certainly it could, but I don't think we're going to cover all of recursion by that time. But certainly you should be comfortable with recursion. Even though we're discussing it in more detail, it is something you've done before. We're simply going to talk about some different definitions in terms of tail recursion, binary recursion, and so forth. But the ideas should not be new. All right. Do any of us remember mathematical induction? Kinda? No? All right. Yes, the theorem. All right. So it's a way, it's a technique for mathematical proofs that allow us to, all right, okay, that's quite enough, that allow us to prove that a statement holds for either all natural numbers or some subset of that, right? By showing that if something works for some base, why do you want stuff like this? So that you can remember, and also helps when thinking of recursion. So usually we'll have a base case. So we'll say that either for 0 or 1 or some natural number that this thing holds, we actually have to prove that. So we have to have some calculation that actually proves that this particular statement holds for 0. Then we assume, well, if it holds for n, and the deductive step, if we can prove that it holds for n plus 1, if it holds for n, so we do some work here. Here we assume. Then it holds for all natural numbers greater than our base. Why does this work? Okay, we don't go any further than that. But why does this work? That's the important part. Well, if I can prove that it works for some base case, let's say 0, and if it works for n, it works for n plus 1, then we can build up to any natural number. Because if it works for 0, that we've proven, and we said if it works for some number, like 0, then it works for 0 plus 1. So it means it works for 1 because it works for 0. It works for 2 because it works for 1. It holds true for 3 because it held true for 2, and so forth. We can build up to any natural number. All right, so it's a great proof. You prove that it works for a certain number. You prove that if it holds for n, it holds for n plus 1, and that proves that it actually works for all natural numbers because you can build up to that. So recursion is analogous to that. With recursion, we have to again have a base case. You have to have some actual either return value or some work done. So you have to return something. Then, if you can express the problem as a recursive call to that method with a, I'm going to say smaller problem, that's kind of a misnomer, but with a smaller problem that moves towards our base case, that's most important, then you're able to have a solution for any problem. So as long as in your recursive call, you're moving towards your base case, then it will work because you've told your method what to do for the base case. However, if your base case is 0, and each time you're doing a recursive call to x plus 1, so you're going to a larger and larger number, then that's not going to work. So as long as you're moving towards your base case, it will work. All right, so analogous in that fashion. And here's simply an example of a recursive method. Do you understand recursion? If not, then call recursion again. Until you do, then you're done. Okay, so the base case is that you do, then you're done. If not, then you do a recursive call in the method, which will again ask you, do you understand recursion? All right, so a recursive method is simply a method that calls itself. Someone's already asked recursion versus loops. There are recursive methods that can be expressed as loops. I will look at ones that are easily expressible as iterative statements, so as loops, but there are also some that can't be. All right. So sometimes, so it is a method that calls itself, and sometimes the solution has repetition. So there's some classic examples of recursive methods. We're going to go through most of them. And actually, the question was asked before is of interest now because what we find is that the Ackermann function actually can't be expressed as an iterative function. So some of them can't be converted to loops. All right, but some more simple ones can be changed to loops. So for us to say every recursive function can be written in an iterative manner is not 100% true. It is computationally true, but there is no expression for us to be able to express an Ackermann function within it. Okay, and a good question. Will the recursive function perform better than the iterative one? Usually, no, it won't actually perform better than the iterative one. Why? Because each time that we are calling that method, each time the method calls itself, a new instance of that method is created. All our local variables have to be created as well. And when that stops execution, it then returns control back to the method that called it. That process takes longer than the same number of iterations within a loop. So the same number of recursive calls compared to iterations will take longer. Usually, it's that it is more elegant. It's a lot simpler to express certain solutions as recursive functions compared to expressing them as iterative functions. All right. So let's look at an example. We'll spend some time here and then I guess end there, as people seem to be full of all the ideas that we looked at. So if we look at Euclid's algorithm, which is an algorithm for finding the greatest common divisor between two numbers. So we have two integers, and we'd like to find the greatest common divisor between them. And the function goes like this. To find the GCD of A and B, if B is equal to 0, so if our second term is 0, then return A. That is the greatest common divisor of A and B. If it's not, then recursively call GCD as B, or rather call GCD with B as the first argument and A mod B as the second argument. Right, are we convinced that this could actually work? Okay, let's just look at one example to quickly see whether it works or not. So let's say we had, okay, I'd like to use things that are a little simple. So let's say 12, but not ones that are multiples of each other because that's a little too simple. Let's say 12 and 15. What's the greatest common divisor of these two? One is always the divisor of any two integers, right? But what is the greatest common divisor of these two? 3, exactly that. So we should get 3 at the end of this. So let's apply the method. It says if B is 0, return A. B is not 0. So now instead we call GCD on, and note, now B becomes the first one. Yes, okay, so that's fine. We have 15 now, and we want 12 mod 15. What is 12 mod 15? Brilliant. All right. So now we end up with something quite similar. We're calling GCD on 15 and 12. Okay, what does that now give us? 12 now becomes our A. And what is 15 mod 12? Now 15 does, 12 does indeed go into, okay, we've already given the answer. Good. So the remainder when you divide 15 by 12 is 3. Okay, it's 1 remainder 3. Now we're calling GCD on this. And we're going to have 3 then becomes our A. And what is 12 mod 3? What's the remainder when you divide 12 by 3? 0. Brilliant. So we call GCD on this. And the rule is if B is equal to 0, then you return 3. So we now end up returning 3. And is that the correct answer? Yes. So yay, it does indeed work. All right. There we have the function itself. GCD int A B. If B is equal to 0, then return A. Just note that those are two equal signs. So if B is equal to 0, not an assignment sign, then we return A. Else, if A is greater than or equal to B and B is greater than 0, then you return the GCD of B and A mod B. Or else you return the GCD of BA. All right, all that does is to make sure that if the one isn't larger than the other, then you swap them when you call the method again. All right, that's essentially what we're doing otherwise. Okay, so that's a nice example of a method that is easily expressible as a recursive method. We see that it does indeed work, and we have an implementation for it that allows us to do that. All right, so we have about 20 slides left. We'll do a few of them so we don't fall behind. What if it worked by fluke? All right, well, you can't prove something by example, you can only disprove it by example, but you can look at different numbers and convince yourself. This is the exact same thing that you do when you're testing a program. There's no way that you can test for every single input. And yes, it may have worked just by a fluke, so your test should not have a single input. Your entire test feature shouldn't be, I test just 2 inputs in this case. You should be testing for many different pairs of integers and convince yourself that does work. For big ones, for small ones, for when we have strange ones like 0, 0, for when we have ones where one is a multiplier of the other, and so forth. All right, then you can be convinced that it does indeed work. So we will just do a couple of slides of this so we don't fall behind. Then we'll have the prac lecture. I will upload the practical before we start the prac lecture. So just after you finish these slides, so that you, if you want to start right away, you can do that. But also so that while we discuss it, you have the code already. All right, because people had some questions, and I think that it would be you would be able to understand easier if you have the code in front of you while we discuss it. All right, are there any questions on what we've covered today? So finishing off W linked lists and beginning on recursion. Could you repeat when you will release the prac? Okay, so when we're done with the slides on recursion, before we get started on the prac lecture, I'll release the prac so that you have the code when we're discussing what needs to be done for that prac. Okay, previously I released it after our discussion, just before you get started, but instead we're going to do it so that you have the code while we're discussing it. Could you traverse through a tree ADT using recursion? Well, what type of traverse are you trying to do? If you're trying to do something like a binary search, then yes, you do. It's easily expressed using a recursive method. Let's see, if you're trying to do a depth first search, yes, then you do still express that as you could easily express that as a recursive method. You simply have your base case that you return. If it's a leaf, then you return that. If not, then you call that on all its children. So you'd be calling it on sets of nodes. So it wouldn't look too pretty. But if we were to put those sets of nodes into something like a linked list, which we already have, then you could, in a nice, legible way, create a recursive method that does that for you. But we will get to that. How do you move the cursor around in a circular linked list? All you do is, when you're done with that particular node, you say that cursor is equal to cursor.getNext. That then advances it 1 position. And because it's a circular linked list, because we have that link from the last node to the first one, there will always be a next, as long as your list isn't empty. So you should obviously check, is cursor equal to null? If it is, then it's empty, you don't do anything. But as long as there's a single node, then each time you go to next, or if there's a single node, you'll simply go back to that same node. But as long as there's 1 or more nodes, you can go on to the next node by making cursor equal to cursor.next or .getNext. If we want more information on where we went wrong for a prac, can we contact our marker on Discord? Yes. I see that Eve actually does now show you which group and session you've been assigned to and who the marker for that one is. So the markers will be available, as I said yesterday, during the first period of our practical session. So that's during TH8, just after our prac lecture, from 1350 to 1435. You may direct message them. That's what they're there for. And you can ask questions about where you went wrong. Tomorrow's practice about single linked list. Yes, that's what I've already said. Oh, yes, you could be asked any of those things. Okay, but I've already told you that. How we know their usernames? They're using initial and last name as their username within that server, as an alias within our Computer Science 3A server. So they'll be exactly what you see on Eve. That'll be their username on Discord. They also have a different role of assistant, so you should see them above everybody else in yellow, so that'll make it a little easy as well. All right, so we'll end there. Thank you very much. And we will continue right from where we left off tomorrow, and then get straight into the practical lecture, and then you'll have your time to do the prac. Note, I've discussed with Pathfinder Har. I decided that we will make the 6 p.m. submission standard for all the practicals. So you will get an additional hour of submission time, whereas usually it's due at 5 o'clock. Because you're all working remotely and may have some issues, we give you the additional submission time. The session still ends at 5, so make sure that if you have any questions, you ask them by 5 p.m., but you have until 6 p.m. to submit on Eve. Can you upload for us problems that have a bit of flavor of the problems we'll solve tomorrow? No, certainly not. A student already mentioned, or at least asked, is it something similar to LeetCode? And although the questions aren't going to be like that, it's the same type of thing. You're trying to solve problems. So whether you're going to go and look at small questions like that in LeetCode, or you're going to go ahead and do the exercises that we've given you at the end of each chapter, those are both good ways to prepare. All right, someone missed what I said about the prac. You will have until 6 p.m. to submit your pracs every week. Is tomorrow's prac more or less difficult than the first prac? It is similar, so it should be easier for you because you did something similar last week. All right, it's a minute before the next period begins, so I'll end there. Thank you very much, and I'll see you tomorrow.